In this slidecast, we'll cover maps and multi-maps. Map is related to set. Mathematically, a map is a set of ordered pairs whose elements are known as the key and the value. Keys must be unique, values need not be unique. So you can think of a key as a mapping to a particular value. Now, a map provides an efficient storage and retrieval of information in a table, and a map can have many-to-one mappings. For instance, B can be mapped to Bill, and B2 can also be mapped to Bill. So here's an example of the key set where the keys are unique, and then the value set, and values need not be unique. Now, an onto mapping, all the elements of values have a corresponding member in keys. So a map can be used to enable efficient storage and retrieval of information in a table. The key is a unique identification value associated with each item stored in the table. The value in the key-value pair might be an object or even a pointer to an object, with the objects in the class distinguished by some attribute associated with the key that is then mapped to the value. When information about an item is stored in a table, the information should have a unique ID. And a unique ID may or may not be a number. This unique ID is equivalent to a key. And here are some examples. If we have university students, then the key could be the student ID number. And here are the values that could be associated with it: the student's name, address, major, etc. In an online store, email addresses might be the unique key that identify customers. In an inventory, we could have part IDs that would be unique to each part. Now, in comparing maps to indexed collections, you can think of keys as selecting the elements of a map, just as indexes select elements in a vector object. Now, the keys for a map can have arbitrary values, not just integers such as 0, 1, 2. So the subscript operator is overloaded for the map class, so you can have statements of this form. Here we assign to V the value for key K. So if we have a map and we use K, the key, as the subscript, that will go into the map and it will pull out the value associated with that key, and that's what gets assigned to V. And this assignment statement sets the value for the key K to be associated with the value V1. Okay, now K is the key type, and V and V1 are the value type. And the variable, a map, it's of type map. A map is effectively defined as a set whose items are pairs. And the member functions for both are the same except for the type of the parameters. Now, the map is a template class, and it takes the following template parameters: a key type, which is the type of the keys contained in the set; a value type, which is a type of the values in the value set; compare, which is a function class that determines the ordering of the keys. By default, it's the less than operator. And the allocator is the memory allocator for key objects, and we'll use the library supplied default. Now, items are stored in a map ordered by their compare function. If you use an iterator to iterate through a map, you'll get a sorted list of the contents according to this compare function. And the compare function is used to create the function class key compare, which compares only the key type part of the pair. Remember, the pair consists of keys and values. And this together they're called entry type, and that's what's stored in the map. So the key for an entry can't be changed, but the value can. So here is this struct key compare, which is a function struct which takes a left and a right entry type, and notice its implementation is simply the less than comparison between the first items in the entry type. And remember, first corresponds to the keys, second is the values. The map functions are all implemented by delegation to the corresponding set functions. And in addition, the map class overloads the subscript operator so that the key can be used as an index. Remember, we saw the case where you can have a map variable and you can use the subscript with k with some key value to do a lookup in the map. So for this reason, a map is also known as an associative array. You can use this kind of a reference to input the key in the subscripts in order to return the value for that key. Here's the code that overloads the subscript operator. It's placed at the end of the public part of the class definition, and it begins as follows. And this is rather complicated. So here we're overloading the operator. We take in a key as the parameter. It's a const reference. Now what happens here, we've got a call to the set.insert, and the set is the private variable in the map class. And so we'll insert an entry type which has the key, and then here is whatever kinds of values are in our map. Here's the default, this references the default constructor for that value type. So what insert will attempt to do is to add a new entry with that key and a default value. And you need to go back to the prior section in this chapter. Maybe you should pause here and go back and read about this insert method. I mean, it's a rather complicated method, but remember what happens is if you try to insert a key that doesn't exist, then this insertion will succeed, and what you'll get back is a pair that contains an iterator, which will first point to that new key you've just added, and a Boolean value which will be true. So if the insert succeeds, an iterator that will point to the key just added and the Boolean set to true. Now if this key already exists in the map, then the insertion will fail, and you'll get an iterator that points to the key that's already, the entry that's already in the map, and Boolean will be set to false. So this code, when you do the subscript and you're trying to do an associative access, look up the value for a given key, it attempts to just insert that key, and you'll get back a pair that will depend on whether you added the key or whether a key value pair already exists for that key. Now, because changing a value that's in a set could disrupt the ordering of the item, the iterator's dereferencing operator always returns a const reference to the object. So we need to return a non-const reference to the value type part of the entry type object. So we need a const cast to remove that const qualification. And here's the code to do this. So remember RET, let's back up. Remember RET was the local variable to where we're going to assign the result of this insert. So let's go forward. So ret.first points to the first item of this set, which is the iterator. And if we have the dereferencing operator, that's going to get the first item that iterator points to. So that's going to be an entry type. And it'll be a const reference, and so here this const cast is going to remove that const qualification. So now we'll have an entry type that's not const. So here is the map.h file. We have our entry type, which is a pair for our keys and values. Here's our key compare function. Kind of a function, it's a struct that gives our function to compare the keys. We have some methods dealing with the iterators. If we go on further, here's this overloaded subscript operator where we first try to insert the key into the set, and we're going to get back a pair, and it will differ depending on whether that key already existed. Then we'll go ahead and get a non-const entry type, and then we'll return entry.second. And so second is the value. So when we go ahead and do this subscripting operation, if the key value pair already exists in the set, we'll get a reference to its associated value. If it didn't exist in the set, then we will have added kind of a default value type, and that's what will be returned from the subscript operation. Now the following statements build a map object. So we can declare this local variable map, and then we can take the string Jane and assign it to map location J. So notice here, when we evaluate this, since J doesn't already exist in the set, remember we'll get an entry with sort of a default value for the value type, and it'll be non-const so that we can then assign Jane to it, and so forth. So here we'll assign, for each of these keys, we'll assign these associated values, and notice we'll get two keys B and B2 will both say be associated with the string Bill. And here's a way we can output the keys and values. If we say Bill maps to, and we say a map and with the string Bill, then that will display Bill maps to. And a side effect of this statement is that Bill would now be a key in the map associated with the empty string. So in section 8.4, we used binary search trees to store an index of words occurring in a term paper. Every element in the binary tree consisted of a word followed by a 3-digit line number. Now, if we store the index in a map, we can store all the line number occurrences for a word in a single index entry. Every time a word's encountered, its list of line numbers is retrieved using the word as a key, and the most recent line number is appended to this list. So here's our build index function. The precondition is index is an empty map. Following the function, the lowercase form of each word with all of its line numbers is stored in the index. In is an input stream attached to the data file, and index is the index. And we initialize line number to 0, and then as long as we're getting each line we get, we increment line number. Then we create a string tokenizer for the current data line using punctuation and white spaces as the delimiters. And then every time we extract a token, then we can go ahead and use the subscripting operator to insert the line number to be associated with each word as the key. So a given key can have one or more line numbers associated with it. Now assume that we want to use the class person with data fields family name and given name to be the key in the map, and then family name should determine the ordering of person objects. Now if two persons have the same family name, then we need to use the given name. So here's our compare person, sort of a function structure. It takes P1 and P2 each as a reference to a person object, and we first compare the family names, and if P1's family name is less than P2's family name, we return true. Otherwise, if the family names are equal and the given name in P1 is less than P2, we'll return the Boolean result of this expression will be returned as the result of the comparison of these two person objects. Now, like the multi-set, the multi-map removes the restriction that keys are unique, and the subscript operator is not defined for the multi-map. Instead, we have lower bound and upper bound in order to get a range of iterators that reference the values mapped to a given key. Here's a print index function for a multi-map called index, and we can get an iterator that starts at the beginning, and we print words. Then we print the rest of the line numbers by having a multi-map next word. We first set equal to the upper band, and then as long as we can continue to get words, we'll output them. And that brings us to the end of this slidecast.